Okay, on our Blackboard site under lab material, there's a new lab that just got posted, Lab 2. For this one, it's going to be more of a fill-in than the previous one because there's a lot more numbers to copy and paste. And it's just going to be easier to fill it in and hand it in more of a typed format. Okay, so in this lab, we're still going to be using WebMO, but this time we're going to be evaluating computational cost versus accuracy. Right, so I've selected a couple molecules. I think they are varied enough in size that you should be able to see a difference in how long it takes to calculate them. Okay, I'm going to go, so what we're going to do is we're going to calculate a carbon atom by itself, a hydrogen atom by itself, then the hydrogen molecule, methane, ethane, propane, butane. I think that going from methane to butane, we should see enough of a difference to really get a decent idea of how long these things take. Hopefully there won't be the confounding factor of multiple people submitting jobs and that adjusting time. I set it so that on the WebMO server, so that every job that we submit is handled by one processor. So we shouldn't have scaling of processors, which is why the different jobs were taking different lengths of time last time. So hopefully, fingers crossed, you'll get an accurate idea of computational cost versus size of molecule and basis set. So we have the level of theory. We're going to be using the B3LIP just like we did last time, but there's a whole bunch of other ones that have different degrees of accuracy. Right? So a lot of times, and I think at the end of the semester we're going to be manually doing a Hartree-Fock calculation, an HF. Those are sort of the most basic level. It's what's called an ab initio. Ab initio is Latin first principles. The other types of calculations, the B3LIP, are density functional theory. When Kieran gets back, we'll have a lab in which we're going through all the minutia of that. So for this lab, we're going to be using B3LIP. You're going to first select the STO3G. This is the lowest, the simplest basis set, and then as you progress across, you can see that the alphabet soup gets bigger, which means more calculations or more functions are being put into your calculation, and so it should take longer and longer to do. So you're going to be recording the value of the enthalpy in Hartree's, the calculation time for each one of these. I would suggest plugging them into Excel because we're going to actually do some manipulations with them. Now, in order to make it so that the calculations are, the calculation times are a fair comparison, the first thing we're going to do for the molecules is we're going to make the molecules do the molecular dynamics optimization, which is the thing that looks like a wrench in WebMO. Then take that structure and run a energy calculation, right? So what that will do for us is it will put in our job queue a structure that we can then use as our starting point for all the others. So they're all going to then be starting from the same structure. If you manually make them each time, they're going to be slightly different. And the amount of time it takes to do a calculation really depends on your starting structure. So by doing what we're going to do, it makes it so that they're all starting from the same structure, and so we can say it takes this amount of time to get from structure A to the end structure for all of them. So it's an equal comparison for everything. Does that make sense? Okay. Then we're going to use the values to calculate atomization energies and enthalpies of reaction. Atomization energies are similar to enthalpy of formation. So you might remember from general chemistry or some other chem, the enthalpy of formation is the amount of energy that it takes to form the molecule from its constituent elements in their most stable elemental form. So that would be hydrogen as a gas, H2, and then carbon in the form of graphite. The problem is it's kind of difficult to calculate using computational means graphite. Right? Graphite is a planar repeating series of carbon atoms. You know, it kind of looks like a benzene plate. It's fairly large, and so it would be very computationally intensive to do. So the way that a lot of times people find enthalpy of formation values is we do atomization energies, which instead of going to the elements in their most stable elemental form, it's the individual atoms by themselves in the gas phase, right? If you remember your MO diagrams, or, well, I guess it wouldn't be MO because it's a single atom. Your energy diagrams where you have 1s, 2s, 2p, right? If we're talking for the hydrogen atom, you have a single electron, and this can be sort of your arrow pointed up or down. And so the spin multiplicity for hydrogen would have a multiplicity that's equal to 2. You can have it either up or down. For carbon, right, you have a total of 6 electrons, and by Hund's rule and the Aufbau principle and all that good stuff, this is what it looks like, right? So for this one, they can be both spin up, a mix, or both spin down. So the multiplicity of carbon is going to be 3, right, for a carbon atom. So that's what here I mean by the molt equals 3, molt equals 2. Where that's going to come into effect, why don't we log in to our WebMO server. Actually, I should probably. So over the weekend, the people who are taking care of our server did an update, and it actually wiped out all of the jobs that we had run last time, which is why the queue is fairly clear. I was running some of them today to look at calculation times. So let's do the first one, which would be a carbon atom. So if you remember, you do your periodic table, select carbon, and then just hit. Don't click and drag anywhere. We just want the carbon atom, nothing else. Go over here to continue. Okay. Now, when we're doing the molecules, we're going to run molecular energy calculation so we can save that starting geometry. But for the carbon and the hydrogen, there's no bonds to adjust, and so there's no real optimization that gets made. So for these, for all your different levels of theory, you can just start with that single carbon dot, the single hydrogen dot, and progress. You don't have to do the molecular energy to have a saved structure. Okay, so we would do, we're just going to do a geometry optimization. This week we're not going to be worrying about the frequencies. Okay, change this to V3 lip. And then you're going to change this to minimal to STO. Now, here where it says multiplicity. For carbon, we're going to make that, it'll either be 3 or triplet. Okay, and then again, we're going to use for our job names, start out with your initials, dash, and then the chemical formula or whatever, however you want to call it. Okay. Let's make sure there's nothing else. No, we're going to click run. Good. That all took 1.3 seconds. So hopefully the alterations in time got accounted for. Okay, so we have our value, and that's what you're going to use for your carbon atom. So what you'll do is you click on this, scroll down, grab the UB3LYP energy. And you're going to paste that, so you can just copy and paste it into your, I would make an Excel spreadsheet from the lab 2 document. But you'll end up pasting that value right here. And then you'll go back to well, there's two places where you'll find the calculation time. One is going to be on the web MO job manager. The other place is we can actually look at the file itself. So if you click on the raw output, so right here, click right here under raw output. Now we'll actually open up the output file in a version that you can view. So this is what the output file actually looks like. A couple parts that will be helpful. So first thing, it lists all the people that are involved in creating the program, and then here it tells you what version of Gaussian you're running. So the WebMO server, what it does is it creates an input file and then runs it through Gaussian, which is a separate program. It's the Gaussian that actually does the calculations. This part here, that's immediately after the version of Gaussian, is your input commands. So this is the type of calculation you're going to be running. So you'll see it says B3lip / STO-3G OPT is for an optimization. Right? So if you forget what type of calculation you did and you're looking at an output file, you can just click on See Raw, scroll down right after the names, and that'll tell you what type of calculation you did. Okay. If we go all the way to the bottom, so some of these files can be fairly long, and so doing the regular scrolling, is best to grab the bar on the right and drag down to the bottom. Okay, so right down here, at the very end, it has the length of time that it took, and that's in CPU time. So if you had 2 processors, it would double the actual time that it took, right? Because each CPU is running it, and so let's say you're running it on 2 processors and it took a minute. The value you would see is 2 minutes because it took a minute of 2 different processors. So the total CPU time is the sum of the time that it's spent on all the CPUs. Okay? So you can write down the 1.3 here, or if you go back to this and you go to your job manager, over here it also has how long it took. But when we're in a couple weeks, we're actually going to start using Gaussian alone without going through the WebMO interface. We'll be using Gauss View to give you an idea of different computational things. For that, we'll be going in and looking at the raw output files a little bit more. So this is where you can find some of this information that will be helpful. The reason why it's good to get an idea of how long things take is you can imagine as you make bigger and bigger molecules, you need to know how long your job's going to take so you can decide what level of theory you want to do. That's essentially what we're getting at today is accuracy versus time. That's the point of today's lab. Okay, so you're going to write that number down, the 1.2. Or sorry, 1.3 seconds down here. So the values in this column are Hartrees, the values in this column are seconds. Record all these. Once you guys get to fairly far in that, having filled this table out, then we're gonna jump to the next table of how we're gonna use those values to compare to actual literature numbers. Okay, so make up your molecules and start getting them running.